Hi all. Sorry I've caught whatever's been going around and I'm home today not feeling great. But I did want to continue our notes, so we're going to pick up with note 6E, and we're going back to confidence intervals for a difference in population proportions. We use this when we want to compare two populations or two treatments in an experiment. And we do this by looking at the difference between the two groups, P1 minus P2. If the difference is equal to 0, then we say the populations or treatments are equal. And if the difference is not 0, the populations or treatments are different. We can estimate a difference in proportions using the same method we used for a single proportion, with minor changes to how we verify the conditions. So same state plan do conclude, except now the conditions I have to check both groups, and my margin of error has to account for both groups. So let's take a look at the moving pieces, and then we'll do some confidence intervals. So first, we know that when we're checking conditions for proportions, we're checking random, independent, and normal. So for random, we're scanning the word problem. We're checking to make sure, one, that our samples are independent of each other, and two, that both samples are random, or that if we're doing an experiment, we used random assignment. For independent, ideally we want to use sampling with replacement, but in reality, as statisticians, we know we don't do that very often. So we want to check that the 10% condition is met for both samples. So if I'm pulling two samples from two different populations, I have to check each sample compared to its population and make sure that it's less than 10% of its population size. We have a similar idea for normal. We know that I want to make sure that my sampling distribution of sample proportions is normal, that we perform the large counts check. Number of successes, number of failures is both bigger than 10. In this case, I have to do the large count check for both samples and their corresponding proportions. So now on to calculating our confidence interval. So remember, oops, sorry about that. That is not what I meant to happen there. I just had a brain fart. Remember, when calculating our confidence interval, our sample statistic is the center of that interval. And in this case, because I'm looking at a difference in population and proportions, my sample statistic is going to be the difference in sample proportions. So p hat 1 minus p hat 2. We also know that our confidence interval depends on the sample size and sample proportions for, oh my gosh, why did I have a brain fart there? I know my confidence interval depends on that sample statistic, and it depends on our margin of error, which has two moving pieces. It has a critical value, which will stay the same, and a standard error formula, which will change because now I need to account for both samples in my standard error formula. So our new standard error formula our standard error for p hat minus p hat is the square root, and this is going to be a big one, of p hat 1 times q hat 1 over n1 plus p hat 2 q hat 2 over n2. I guess not that big. My hope is that doesn't look too scary, because we notice that each of those individual fractions is the standard error for a single proportion, and now we're just adding them together under the square root. It doesn't look pretty, but it hopefully looks familiar. Substituting those changes into our confidence interval formula, we get p hat 1 minus, p hat 2 plus or minus z star times square root of p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. Again, a little bit more complicated, but hopefully familiar. We know that our calculator can help us, and I don't know why I said distribution menu. We know it's not the distribution menu. We know it's the stats test menu. And there should be, just like we had a 1 prop z int, there will be a 2 prop z int function on our calculator. Reminders, we should still set up this formula on our paper before we use the calculator function to help us. I'd like to use the rest of the video to just do some examples so we can see how this works. If you have questions, feel free to email me so I can clarify. Okay, so first example says patients with lower back pain are often given non-steroidal anti-inflammatory drugs, NSAIDs, like naproxen, to help ease their pain. Researchers wonder if taking Valium along with the naproxen would affect pain relief. To find out, they recruited 112 patients with severe lower back pain and randomly assigned them to one of two treatments, naproxen or Valium, or naproxen and placebo. After 1 week, 39 of the 57 subjects who took naproxen and Valium reported reduced lower back pain, compared with 43 of the 55 subjects in the naproxen and placebo group. Construct and interpret a 99% confidence interval for the difference in proportion of patients, like the ones in this study, who would report reduced lower back pain after taking naproxen and Valium versus after taking naproxen and placebo for a week. Based on the confidence interval, what conclusion would you make about whether Valium along with naproxen affects pain relief? Justify your answer. So, two things. First, construct and interpret a 99% confidence interval. So we know how to do that. They told us it's for a difference in proportion. So very first thing I'm going to do in my state step is define those population proportions and then identify the other numbers I've given in the problem. So in the problem, when they gave me my sample data, they gave me the naproxen and Valium group first, and then the naproxen and placebo group second. And so that's how I'm going to define my portions here. So this is the population proportion of patients on naproxen plus Valium with pain relief and then 2 is the population proportion of patients on naproxen plus placebo with pain relief. And you will notice I am using quotes because a lot of that is similar. We're really only changing Valium versus placebo. For my state step, I should go through and identify everything that I was given. So I know that I have two groups. I have number of successes and sample size for group 1. So for group 1, we're told 57 subjects took both naproxen and Valium, and that 39 of them reported pain relief. For group 2, we had a sample of 55 subjects, 55 patients, and 43 of them reported pain relief. The only other number I really need to record here is my confidence level. So my confidence level for this problem is 99%. So that is my state step. Next, I'm going to do the plan step. So I am building a 2 proportion Z interval. And I know that means I need to check 3 things: random, independent, and normal. So we'll start with random. And if I go back up here, it says they recruited 112 patients with severe lower back pain and randomly assigned them to one of 2 treatment groups. So random assignment was used. Next is independent. So independent is 10% condition for both. So our first sample size was 57 patients with back pain, which is safe to assume that that is less than 10% of all patients with back pain. And we get a similar statement for the next one. Our second sample size was, did I do that backwards? Oh, I did. 57. No, I didn't. 55. There we go. 55. And it's a similar statement. Patients with back pain, less than or equal to 10% of all patients with back pain. And yes, I am cheating with technology. Don't judge me. So 10% condition on both samples. And my last is normal. And we check the normal condition with large counts for both samples. So I'm going to make 2 little blurbies here. So I want number of successes and number of failures. So for sample group 1, we had 39 successes out of 57 patients. So 39 is greater than or equal to 10. I'm happy. 57 minus 39 would be 18, which is also greater than or equal to 10. So sample 1 clears that bar. For group 2, we had 43 patients with pain relief, which is greater than or equal to 10. And I had 55 patients. 55 minus 43 would be 12, which is also greater than or equal to 10. So we clear that bar in both samples. From here, we're going to build our confidence interval. So we know that our confidence interval is p hat 1 minus p hat 2 plus or minus z star times our standard error, p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. In order to plug those numbers in, I need to know what my z star is. And you can see I'm running out of space down here, so I'm going to go back up to our plan stage, and I'm going to do my z star off to the side up here. So to find our critical value, we know we draw a normal curve, zero in the middle, 3 hash marks out in either direction. And then we shade in the area for our confidence level. So we want to be 99% confident, which is past the 2 standard deviation hash mark, because I know 2 standard deviations is 95% of my data, but it's inside of 3 standard deviations, which is 99.7. So I'm going to make my little hash marks just inside of 3 standard deviations and shade in that area. And we know that should be 99% or 0.99. And then we're going to pull up normal or inverse normal on our calculator to calculate that. So second vars, inverse normal, and you'll notice mine doesn't have a tail, so I need to give it the left tail. Mine assumes left tail. You guys can do 0.99 and then center as your tail. If I have 99 in the middle, 1% in the tails, half of that is 0.005. Remember, we're assuming standard normal, so mean is 0, standard deviation's 1. And we get 2.58, which should sound familiar because we've seen that with a 99% interval before. So 2.58. So we can come back down in here, start plugging in our values. So I don't have p hat 1 and p hat 2, but I have the information for it. So p hat 1 is x over n, 39 out of 57. P hat 2 is 43 out of 55. not plus, minus, Mr. J. And then plus or minus square root. And here's where knowing what those are would be helpful. Let's plug that in a calculator. Ah, that is not what I meant to do. Technology is not always my friend. No, stop that. There we go. So we want 39 out of 57. So for that first proportion, we're going to have 0.68. And then the complement, which would be 0.32 over a sample size of 57 plus, and then the second one is 43 divided by 50, not 73, 43 divided by 55, and we get 0.78. Running out of room here, 0.22 divided by 55. And oh my gosh, what did I forget to write in there? I forgot to write in my Z star. And I don't have students to call me on my nonsense today, so let's shrink that down. Thank you for your patience with my poor little sick addled brain. Plus or minus, and our Z star was 2.58. So we can either plug this into our calculator as it sits, or we can pull up 2 prop z int. So let's go ahead and do 2 prop z int so we can see what that looks like on your calculator. Ooh, that works. So stat tests, and 2 prop z int is going to be somewhere down towards the bottom. Option B, right beneath 1 prop z int, asks us for similar information. Whoops. So we had 39 successes out of 57 for our first sample. We had 43 successes out of 55 for our second sample. We had a 99% confidence interval, and we calculate. And my calculator is spitting out negative 0.311 to positive 0.116. And that's the do stage in its entirety right there. We wrote out the equation, we showed the substitution, we have our answer. We do know the last thing I need to do is interpret that answer. And we know for confidence intervals, we say we are 99% confident that the interval from negative 0.311 to 0.116 captures the true difference in proportions of patients who saw pain relief from, and then the treatment, so naproxen plus Valium versus naproxen plus placebo. I'm going to zoom out so we can look at that process, and the hope is that feels familiar. We know that that is our confidence interval process. State, plan, do, conclude. State, plan, do, conclude. That was answer A. Answer B then asks, based on the confidence interval in part A, what conclusion would you make about whether taking Valium along with naproxen affects pain relief? Justify your answer. So I'm going to come down here. I'm going to label this my answer to A. And for B, they're asking, can we tell based on that interval if taking naproxen with Valium was noticeably different than taking naproxen with a placebo? So remember, if I scroll back up to that first page, if the difference is equal to 0, the population difference, or the populations or treatments are equal. There's no difference there. If the difference is not equal to 0, the populations or treatments are different. So the question is 0 contained in my interval? If it is, I cannot state that the treatments are different. If 0 is not in my interval, I can state that the treatments are different. So we're looking to see if 0 is inside our interval. And if I look, lower bound is negative, upper bound is positive, 0 is in between those numbers. So because our confidence interval contains 0, we cannot conclude that Valium plus, or naproxen plus Valium is better than naproxen alone. I'm hoping that feels familiar. We saw those sentence frames and those ideas in our FRAPPy in our last class meeting. And we know for particularly A, interpreting confidence interval, that sentence frame is word for word exactly what the AP board is looking for. Okay, we're going to try one more together, and then I'm going to have you do the last one in your small groups on your own, and we'll check it together on Monday. So let's take a look at our second example. It says the Pew Research Center investigated the views and opinions of a random sample of U.S. adults about climate change. One question in the study was, do you expect that in your lifetime you will have to make major sacrifices in your everyday life because of global climate change? Of 3,646 respondents who were younger than 50, 27.6 expected to make such sacrifices. Of 5,187 respondents 50 or older, 17% expected to make such sacrifices. Even though a single random sample was selected, it is reasonable to consider these as independent random samples of U.S. adults in these age groups. Construct and interpret a 95% confidence interval for the difference, younger than 50, 50 and older, in the proportion of U.S. adults who expect to make major sacrifices in their everyday life because of global climate change. based on that confidence interval in A, is there convincing evidence of a difference in proportions of all U.S. adults in these age groups who would expect to make a major sacrifice because of global climate change? Justify your answer. So we're asked to do a 95% confidence interval for the proportion who believe that they'll have to make major sacrifices due to climate change, and our two groups are age-based, younger than 50, 50 and older, and then check whether we have enough evidence to support a difference. So we're experts at this process now. State plan do conclude. We're going to define our proportions, P1, P2. I'm going to do it in the order they were mentioned. They did mention younger than 50 first. So population proportion of U.S. adults younger than 50 I'm going to have to make more room here, who believe they will need to make sacrifices due to climate change. Sacrifices, I know how to spell. P2 is the same of U.S. adults 50 or older I'm not rewriting the whole thing. It's the same but 50 or older. I need to identify the information I was given, and in this case I was given sample proportions. I was given a p hat 1 and I was given an n1. I was given a p hat 2 and an n2. And we'll go ahead and write these here. So younger than 50, we had a proportion of 0.276 and a sample size of 3646. For p hat 2 n2, it was 0.17 with a sample size of 5187. I'm going to do two more things here. First, I know that when I go to use my calculator function, I want a number of successes instead of a proportion. So I'm going to calculate x here. That's also going to help me make my large counts check. And I'm going to calculate my critical value. And to do that, I need to jot down my confidence level. So I know my confidence level CL is 95%, so 0.95. So here, x1 is p hat 1 over n1. Not p hat 1 over n1, p hat times n times p hat. Why am I having such a brain fart today? n1 p hat 1. And I'm going to use the calculator off the screen this time in hopes that it goes faster because my tech is just not cooperating today. So 0.276 times 3646, and I get 1006.2 something, so I'm going to round that down to 1006 because I know I need a whole number. Down here, x2 is going to be n2 p hat 2, So 0.17 times 5187, and I get 88.17, so I'm going to round that up to 882. I'm also going to jot down my number of failures just so that later I don't have to think about it, because I don't want to have to do the math more than necessary. So 5187 minus 882, so we can get our number of failures at the same time. So 3646 minus 1006. So first group had 2640 failures, and then 5187 minus 882. Second group had 4305 failures. I'm going to quick do my confidence level. So, whoops, that is a horrible bell curve, Mr. J. That's still a horrible bell curve. Z star, 0, 1, 2, 3, 1, 2, 3. I know that 95% sits at about 2. And even without inverse norm, I know that my Z star is going to be 1.96, because we've done 95% confidence intervals multiple times at this point. But definitely check on your calculator. Inverse norm with a center area of 95 should spit out 1.96, which checks with our empirical rule. It's about 2. Okay, next step is the plan stage. So we're doing a 2 prop Z interval. I need to check 3 things in order to do that. Random, independent, normal. So for random, we are told that random sampling was used. It says even though a single random sample was selected. So we are told random sampling was used. For independent, we do the 10% check. So we're expecting that 346 is less than or equal to 10% of all U.S. adults younger than 50. Which is a reasonable assumption. We also need to check that 5,187 is less than or equal to 10% of all U.S. adults 50 or older, which again is a reasonable assumption. Normal, we're checking both successes and failures. So number of successes, number of failures, number of successes, number of failures for second group. And we calculated those up here. So for group 1, I had 1,106 successes, and I had 2,640 failures. For group 2, I had 882 successes, 4,305 failures. So all of those are greater than or equal to 10 by a lot. So we very much clear that bar. We have no concerns on the normal front. So we know that our sampling distribution of a difference in sampling proportions will be normal, which is why I'm allowed to use this as my critical value. Next step is the do. We're going to grab our formula, do some plug and chug. So p hat 1 minus p hat 2 plus or minus z star times p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. So for our sample proportions, 0.276 and 0.17. Wait, did I copy that around? 276 and 17. 276. Plus or minus 1.96 times, and then square root, big square root, 0.276, and then its complement, which is 724, all over a sample size of, I go back up, 3646, plus, let me scoochie over here, 0.17, 0.83, all over our second sample size, N2 was 5187. And again, we don't want to do that by hand, so we're going to grab our calculator and run 2propzint. So stat test option B, and we're using the number of successes and our sample size. So 1006 and 3646, and then 882 and 5187. Confidence level is 0.95, and when I run that on my calculator, I get 0.088 to 0.0124 rounded up. So at this stage, we would write our conclusion. We are 95% confident, and I'm not going to finish that sentence frame because you're tired of hearing me write it, that the true that an interval from 0.088 to 0.124 captures the true difference in proportions of people who believe that climate change will require them to make sacrifices between those younger than 50 and those 50 and older. The other thing we were asked to check, if I scroll back up, we had a B, based on that confidence interval, is there convincing evidence of a difference? And the answer is yes. And because, when we look at that interval, if there's no difference in those groups, 0 should be contained in that interval. And if I look at my boundaries, that's positive, meaning 0 is somewhere over here. Because 0 is not in my interval, I have convincing evidence of a difference. Reminder, I'm shortening this because notes and time on the AP test, you would write out the whole statement. Yes, we have convincing evidence of a difference in the proportions between those younger than 50 and 50 and older, because 0 is not contained in our confidence interval. Always more detail is a good thing. All right, there is a third example. I'd like you to try that in your small groups. I'm going to stamp it on Monday. We'll use it as a bell ringer. If you have any questions, send me an email. Otherwise, I will see you on Monday.